my name is Roy Simpson, and I'm a professor of mathematics at Cosumnes River College in Sacramento, California. And this is another proof in my series for proofs in differential calculus, and this is kind of an afterthought from the proof that the limit as theta goes to 0 of sine of theta over theta is equal to 1. But this one is necessary for future proofs, so we have to kind of prove this guy too. So this is the limit as theta goes to 0 of cosine of theta minus 1 over theta being equal to 0. There are a couple things that we'll need to know prior to starting this, and those are, let me go ahead and switch pages here. There we go. Our prereq knowledge. You have to know limits. You have to be very comfortable with limits. And obviously, what I mentioned earlier, or just a moment ago, you have to remember that we've just proven this limit right here. If you haven't seen that proof, I highly recommend. It's one of the more entertaining proofs that I've done. It's just a fun proof. So look for that. It should be the video in the playlist right before this video. Just for a change, I am going to go ahead and do this proof on this page directly. So we'll just go ahead and write proof in here. And what we're going to do is start with the left-hand side of this, the limit as theta goes to 0 of the cosine of theta minus 1 all over theta. And now a cool trick that's often used within calculus, if you don't know what to do with a limit, or if you have a limit that's 0 over 0 like this one is currently, a cool trick to do is to multiply top and bottom by a conjugate. In this case, I'm going to multiply top and bottom by the cosine of theta plus 1. And remember that all of that is inside our limit right now. Multiplying like this is not a bad thing because I am not multiplying by 0. That's good. And cosine of theta plus 1 over cosine of theta plus 1 is just 1. I'm just basically, that stuff in blue is just a fancy way of writing the number 1. So let's see what happens when we multiply this out. You see the numerator is actually a difference of squares, and so that's going to be cosine squared, minus 1. And then the denominator I'm going to leave factored, and that's always a common tactic when working with multiplying top and bottom by something. You always like to leave denominators factored if you can, mainly because they're no use when you multiply them out. They're more useful when you have them factored. Well, let's take a look at this. That cosine squared of theta minus 1 is very close to a trigonometric identity. Maybe I should have had that you must know trig, but that's kind of a prerequisite of calculus. But let's go ahead and write down the trigonometric identity that I'm thinking of. This is known as the Pythagorean identity, and if I subtract 1 from both sides and subtract sine squared from both sides, I will get the actual identity that we're looking at in our numerator of our limit there. So this is going to equal the negative sine squared of theta, which is perfectly fine for me because that's all I care about having is the sine of theta up there. So let's go ahead and exchange this expression in the numerator for negative sine squared of theta. And now let's check to see if we can take this limit yet. If I let theta go to 0, the numerator approaches 0 and the denominator approaches 0. So still got some issues, but maybe we can do some manipulations here. Now the rule of thumb, if you're going to try to split a limit, and when I say split a limit, I mean break it into two different limits. The rule of thumb is try first, and if when you split that limit, one of those splits ends up not being finite, then you have to go back a step. I'll show you what I mean when I do this. So what I'm going to do is factor out the negative first of all and then split this into two different limits. It's incredibly important. So this is the two limits I've split it into. Notice that the numerators, if you multiply those numerators, it is sine squared, and the denominators give me theta times the cosine of theta plus 1. So I've just broken those apart, thrown the negative out front. It's incredibly important at this point to make sure that these limits exist. If they do not exist, I have to go back a step. I'll have to go right back to where I started there and try to think of something else to do. This is the way calculus works, is that if you start splitting limits, you have to check to make sure those limits exist. Well, we have a theorem that I said is a prerequisite for doing this proof. The theorem is that the limit as theta goes to 0 of sine theta over theta will turn into the number 1. So that which I had just highlighted will turn into the number 1. So that's a negative times 1. And then times. And let's hope that this limit on the right-hand side exists. Well, the numerator will be 0. Right? Sine of 0 is 0. The denominator, well, cosine of 0 is actually 1 plus 1, that's 2. Oh, that's perfect. That means that limit turns into 0 over 2. That's an existing number. It's a finite number, it's 0. So this is just negative 1 times 0, or in other words, 0. Once I see, by the way, that this number 0 over 2 exists, that the limit exists, I am now very confident that I can finish out the proof, which I just did. We find out that that turns into 0. So through a chain of equalities, we've shown that the limit as theta approaches 0 of cosine of theta minus 1 over theta is equal to 0. Q, E, D.